bird.
It's there.
Okay, and a note that Martin has moved these recordings to YouTube, and so they will be available for you in perpetuity, I think.
As long as
YouTube.
exists.
Yeah, exactly. Okay, I'm going to turn it over to Martin, and again, please feel free to put your questions in the chat, either directly to me or to everybody, and I think we'll have a little bit of time to sort of have some interaction as well today. Okay,
yes.
Take it away, Master.
Indeed, because there will hopefully be plenty time for people to join in and share their screens and show age models where things go wrong, or tips or strange cores and sites. Hold on, 1 minute.
Just entertaining. And again, we appreciate the financial support of the Earth Rates Research Coordination Network, funded by the National Science Foundation, in subsidizing the costs of this meeting, of this workshop, and GSA's support of student volunteers here to help us, etc. Okay.
Also, a really important announcement, and I can put it in the chat. If you have a student who's attending GSA or wants to attend virtually, Earth Rates does have limited support for students of all undergrad, grad, for attending. So I'll send you the form if you have a student that needs some support. I think it's we pay for registration in both cases. So I'll put that information in the chat.
Thanks for that, Lisa. That's a great.
All right. Okay. Am I sharing the screen now? Okay. Sorry, dinner just came in, so that's why I was. So anyway, can you see my screen? Yeah. Good. Okay. So today we'll go a little bit again through what we very hurriedly did last time. Say some of the practical things of Bacon. We'll based on the questions and remarks that came in, we'll have a little bit more of a look into the really details of what Bacon does, what's underlying it. Then we'll look at Plum. That will by necessity be a bit short, but we'll be covering that. And then it's really the floor is open to everyone. Okay. All right. So let's first go through the questions and remarks that were received. There are quite a few to go through. The first one is that the session, especially at the end, perhaps was too rushed of last week. Sorry about that, and we'll go through it again now, hopefully a bit slower and in more detail. And if you require more detail, let me know, okay? Either in the chat or speak up. Some wanted to have the R Markdown files available as well, and they're now on the website as well. Yeah. And as for resources to understand MCMC, I'm not so sure what resources there are. There are some on YouTube as well. And I have a link here. It's just something I found, but it's not really, I haven't been able to find much that explains MCMC itself. So yeah, it's still, it's a bit of a niche thing, so there's not that many explanations. But we'll perhaps look at it again when we discuss Bacon's process again in a few slides. Okay. Then there was a question about how you account for reservoir corrections in marine records, or for that sake, any records when using Bacon. And we'll then look at that by looking at the DR and DSTD columns that can be added to your CSV file. We'll look at that. So there are extra columns you can enter, for example, to add a reservoir effect. There's a question about how to enter uranium thorium dates, and also how to deal more wider with speleothems. And the simple answer there is if you add a column to your CSV file, a fifth column, which then specifies a 0 for anything uranium thorium, then that will be a cal BP date and will not be calibrated using the radiocarbon calibration curve. So then it should be fine. But that's assuming that these dates are distributed using a normal distribution. Yeah. If there's any other type of distribution, for example, multimodal or asymmetric, then that will become a problem. And we don't currently have a way to deal with that in Bacon. There's also a paper that just came out last year where an enormous amount of speleothem records were age modeled using a whole different set of age modeling techniques. So if you're interested in that, there's the paper here. Okay, good. Also, do you like this circle, or do you prefer me just to use the arrow here? Just a mouse pointer, this one or this fancy circle? Doesn't matter? Okay, I'll use it. So another question was there about how to extract sedimentation rates from various depths as a text file. And for that, it's not provided automatically. But you could do something like this. For example, we'll have a look at the out file, the .out file that comes with each run. And that contains many columns. The first one is the starting age at the top depth. And then you've got lots and lots of columns for each of the accumulation rates or sedimentation times for each of the sections. So you could go into that output file and check what the sedimentation rate is for the depths within the section of interest. But you can also use commands or functions that are available or you can make yourself. For example, you could use the accurate.depth, which is a function within Bacon, which gives you the accumulation rates of all the iterations for the depths of interest. For example, if you want to know all the iterations, give the accumulation rates for each of the iterations for the depth of 20 centimeters, then you can do it accurate.depth of 20. Okay. You can then also put that into a variable acc20 and then assign accurate.depth 20 to that. And then you can ask information about it. You can see what the minimum is, the maximum, things like that. Yeah. And if you want to, so that's just one depth at a time. And if you have a few depths, that's the way you could go. But if you have a whole sequence of depths and you want to know the accumulation rate of each of those depths, you can do that as well. For example, you can make a variable depth, which has a range of depths, whatever depths you are interested in. And then you can make a loop where you have variables which you assign. So you have the minimum accumulation, min.acc. You add some initial value to it. Then max.acc, add an initial value, and median.acc, just add some names I made up. So we have 3 variables that are currently empty. And now we're going to fill them. Yeah. So what we're going to do is we have this whole length, the whole sequence of depths. Yeah. 0, then 3, then 4, then 6, then 7.2, then 8, etc. Okay. So what we're going to do is we're going to make a loop. So we're going to do a for loop, which says for I in 1 to the length of depths. Yeah. And the length of depth is 1, 2, 3, 4, 5, 6, 7, 8, and 10. So 18, I think, is the length. So there's 18 entries in this case in the variable depth. So for I in 1 to 18, do something. Yeah. So this is a loop which is very often used in R. And once you get your head around it, it's very useful. Yeah. So in this loop, I begins as the first entry of depth, which is 0. So for I in where I is 0, then you do a list of commands. Yeah. So first ask for the depth belonging to the first entry. So the first depth, which is 0. We ask for the accurate depth of 0. So you get all the accumulation rates at 0 centimeters depth. And we just put that in a variable, not a new one. Then we use an R function, quantile, which tells you, looks at all the values and gives the quantiles. For example, the lowest 2.5% and the highest 2.5%, and perhaps the median, the 50%. Yeah. So we're asking the quantile for the variable x, and then we ask it for the 0.025, so 2.5%, 97.5%, and 50%. I hope you get that. So now we have, for that one depth, we have all the accumulation rates, but we have then reduced that to 3 values: the minimum 95%, the maximum 95%, so the 95% range, and the median. And now we're going to fill the values that we're interested in. So min.ac, the first entry, is going to be this min-max, but the first value of that. Then the maximum 95% of the accumulation of the first entry is min-max 2, the second entry of this variable. And then we've got the median as well, and the first entry of that will be min-max, the third value. I hope that makes sense. Yeah. So then we've gone through the loop once for I equals 1, which is the first depth. Then I becomes 2. Then the depth becomes 3. So we could do the loop again. So we go to accurate.depth, the second entry of depth, which is 3 centimeters. And then the same process is done. All the accumulation rates are calculated for 3 centimeters depth and put in their corresponding values for the minimum of 95% range, the maximum of 95% range, and the median. All right. And then we go to the next one, 4 centimeters, and then 6 and 7. So we do that repeatedly until we've reached and read and extracted all of the depths. Yeah. So at the end of that loop, you will then have min.ac, and that will have 10 entries for depth 0, 3, 4, 6, 7.2, 8, 9, etc. And for the same for max.ac and for median.ac. Yeah. Now you can simply combine them. You combine the columns. So you column bind first the depth as the first column, then min.ac, then max.ac, and then median.ac. So you make another variable which combines all the information we have, and you put that into a text file. Yeah, you write a table of that new variable and you call it myx.text, and then you just place header equals true, and then you've got a text file somewhere with then 95% ranges and the median. Okay. I think someone has the microphone open. I don't know who it is. So that's one story, but there's also, you can also plot the entire, say, grayscale plots of the accumulation rate against depth or the accumulation rate against time. You don't need to reduce your information to just one value, say the median or the mean, or 2 values, the ranges. Yeah, we have to step away from using just one value to instead use all the values we have to better represent the uncertainty involved in accumulation rates. And those uncertainties can be large, especially if you plot them on the calendar scale. Okay, any questions there? No? Okay.
But Martin, the out files include some accumulation rate information as well, where you don't have to go through the loop.
Yes. Aha. So you could go to the output file, and then if your depth of interest is, say, 25 centimeters depth, you could go to the section in the output file which contains 25 centimeters depth, and then simply use that column and do whatever you want to do with that column, because that's the column that contains the accumulation rates for the section in which 25 centimeters depth lies or lives. Yeah, but then you have to do work anyway, because you have to open the file and find out where that depth is, which column of your file that is.
Okay, thanks.
Yeah. Okay, so here we've got Amora again, watching me do bacon. So if the graphs at the top of the RBacon graphs don't indicate the quality of the model, then why are they provided? Because last time I focused on that we should really not cut away the top panels, right? So we should include them because they carry important information. From what I understand of the graphs, they simply compare the priors to the modeled output, but the modeled output is what matters. If true, then why provide any priors at all? And also some more explanation is required for memory, okay? We'll look into this question in detail, but first of all, the output of the model, of the Bacon model, is based on the data and on the prior, yeah? So the output that we see in the accumulation rates and in the entire model is not just based on the data, it is based partly on the prior information. Yeah, so it is much more transparent if we then also show what that prior information was. And if we kick that out, then we only see the final model and we only see then the dates, but we don't see what prior information was, which is half of the model. Yeah. And again, we look into more details in what Bacon does and how we should be looking at the prior and posterior information in the following slides. Another question is, how do we tell if the Bacon run was acceptable or needs improvement? So there's Bacon, when it spits out the model, it also tells how well the model fits the dates. And for example, if say 90% of the dates overlaps with the model, then the fit is, well, say 90%, no? And if it's a low fit, Bacon will tell us. So that's one bit. So okay, how well does the model fit with the dates? But that's only one bit, yeah? The other bit is how well does it fit the prior information, yeah? And it's not only that, it's also, there also has to be some degree, in most cases, of user or expert evaluation. Yeah, you know your site, and sometimes, well, Bacon might be doing things that might be running in some strange way that does not make sense for the site in question. But if Bacon isn't told about it, or can't be told about it, then you have to do some additional things to get a model that better describes what you think has happened. Yeah, so it's not entirely automatic. In many cases, it will produce a reasonable model, but there will be some sites where you simply have to do more to look at the output, and even if the fit is nice, there might be something that you think can't be true, and then we have to adapt the priors, adapt the settings to get a model that makes more sense to you. Yeah. That said, there's also, we did simulations where we made a whole set of simulated accumulations or simulated sites, and then produced models, Clam models, Bacon models, Bcron. And what we saw is that the Bacon and Bcron both produce very good, very reliable, very reliable quantity or estimates of the uncertainty. Yeah. So in many cases, not all cases, but in many cases, the model uncertainty in those simulations covered the truth. Yeah, because for simulations, we know exactly what happened, but we don't tell Bacon that. We let Bacon try to find the model. And in most of the cases, in most of the times, the truth was encompassed within the reconstructed uncertainty levels. Yeah. So I'm quite happy with how Bacon and Bcron and other Bayesian models in most cases seem to do a good job in producing age models and their uncertainty that seem to be quite robust and realistic. As opposed to, for example, Plum, where the error estimates might be very narrow and the truth might really, and the actual truth might lie outside those narrow, happy age estimates. Yeah. Any further remarks there? No? Okay, now here's another question. Are there specific commands for incorporating prior knowledge on limiting the age ranges of very young dates, which can have high calibrated uncertainties? For example, over the last 3-4 centuries, there's multiple calibrated distributions because of the changes in radiocarbon concentration in the atmosphere. For example, prior knowledge that part of an age range is in fact unrelated to the event of interest and shouldn't be incorporated into the age depth model. Yeah. So, in other words, we have several dates that where you actually don't want to use some of the ranges, but you do want to use some of other ranges that are that seem to be realistic. Yeah. Very good question. And that's also a very, very good case to actually make use of your prior information, because what you're saying here is that some parts of your dates, the model cannot run through it. And that's because you know that your model very likely took a certain route, or and that means it used a certain accumulation rate. So if you're very, very sure that the model should go through some bits, you can set the prior to something very strong. You can say, well, if I want it to go this way, then I set my prior for accumulation rate to something like, for example, I don't know, 5 years per centimeter, and I make the prior very strong, so very peaked. Yeah. Then your model, through the prior information, is forced to go at that slope. Yeah. So that's actually, it's forcing the model. It's not really prior information anymore, but I think that would be the most transparent way to say, okay, I know from other information that my site should have done this and should be ignoring other parts of our, some of our dates. And in that way, we can then use the prior information to get the model to do what we want it to do. But of course, if we're like doing too much, then perhaps the model looks all very fine, but it can't really go the other ways that actually wanted to go. So there's also a danger you might be prescribing the model too much. Yeah. But that's also why you should be showing then the upper panels, because then the user or the reader of your paper can say, oh, okay, this is what I did based on this and this reasoning. Yeah. That's also a reason why age-depth plots should always be in the main paper, I think, and not in supplementary information, because it's often an important part of the reconstruction.
And Martin, I have this is Amy. I have an example of a case like what you were talking about, a visual. So maybe I can show that.
You want to share that?
Sure, I can share that now.
Mm-hmm.
So hopefully everybody can see that. So this is a case from a relatively recent radiocarbon date that is in this complicated period of the calibration curve, where there are complete reversals for a calibrated date of, for a radiocarbon date of 225 years before present plus or minus 30. There are multiple independent possibilities of what that is in terms of calendar ages, with a 0 probability between them. So there's, you know, a strong possibility, and they're pretty much equal. One that the data is around 1650, and one that it's around 70 or 1800. We know, because we have a lead-210 profile, that one of these dates, that the more recent one, is very unlikely, because this sample is several centimeters below the base of where our lead-210 came from, and so that the 1800 date is very unlikely, and that the 1650 is very likely. And so this is what Martin was talking about using our prior information, whether it's, you know, about the sedimentation rate, the setting, other types of dating that we have, to say exclude one of these possibilities. And Martin, if you have anything else to say about that, I would.
Yeah, that's a really nice example. And what I would like to say is that, you could also use our Plum, so the Bayesian age model that combines lead-210 and other dates, and hopefully by using that model you would then automatically arrive at the correct age for that date, hopefully.
Yeah, I should definitely try that. This is pre-Plum. So.
Yeah, so pre-Plum you would then have to play around with the accumulation rate to get this sorted. But now with the Plum, with the lead-210 information, if the lead-210 information is clear enough and doesn't cause any problems, then hopefully it should be able to combine the two and make sense of them.
Yep, exactly.
Yeah, so then you do.
Okay.
Then you wouldn't. Did you have another example you said?
Nope, that's it.
Okay.
I will. I'll stop sharing, but hopefully that's useful. Feel free to ask questions. We can talk about that a little bit more if people have questions in the chat. But this is one of those examples where you can, from your own information, know that one of these dates is not possible.
Okay.
Can I ask a question, or?
Sure.
Absolutely.
This just kind of made me think, if supposing you had something archaeological that might be hard to put an error on, I guess, but I suppose you could come up with an error for some kind of, in this situation you had some kind of archaeological artifact that you could say it was this date, but could you add that into Bacon easily, or?
Yes, so you could add it as a calendar date. So if you have, say, some marker pollen that you say, oh, this is when that pollen type plantation was made historically, then you can add that. What you can't do is say it should be after this or it should be before this. We don't have that built into Bacon. We can only say, okay, at this depth, we have this and this age, plus or minus an error. Yeah.
Okay, yeah, that makes sense. I was thinking like some kind of, there's a building construction that might be between 1750 and 1810, let's say, and then and you could say that's the window that would make sense, and I guess you could put something with a median and a plus or minus, but I don't know if it'd be quite right.
Yes. So yeah, you could. So yeah, I don't know how you would be able to do that in Bacon. You could enter two dates, but you don't know exactly, like for the start and for the end. But that's perhaps a bit too much. But I can't imagine what type of site would that be. So it would be an accumulating site where Bacon could be used. And what is that information in it that tells you the age of that archaeological structure?
Well, I guess I had we don't have to go into too much detail, but I had in mind there's some sites like with mill sites where they know from the construction that the mill dam was before a certain age, maybe, or after a certain age. And it's sort of, they don't have an exact number, but they, based on some expert, they can say, well, they think it predates this date or after this date. And
Yeah. Okay. Yeah, that will be fun. And currently with Bacon, we can't do that. We can only enter, say, a date, a CalWP date plus or minus a number, an error. But there's also this coffee package where you can say, okay, it should be older than this, or well, I hope that soon you'll be able to. And if there's enough interest, we might want to include such things in Bacon as well, but I haven't seen much case for that yet.
okay, yeah, it was more of a hypothetical question, not.
Yeah,
Yeah,
that's a good one. Yeah.
okay, thanks.
Yes. Okay. But actually, so we'll look into how to set the prior, how to work with that in order to get your model to do something, but then remaining transparent about that. Okay. Of course, you can't be fudging your model too much. Of course, then it becomes wishful thinking. Okay. Right. So I think so. We need to step back a bit and then look at what Bacon actually does. So what's the underlying age depth model of Bacon? Yeah. So what it does here in the graph, you've got depth on the horizontal scale and age on the vertical scale. That's because my maths colleague doesn't like it the other way around. So that's how I work. But okay, anyway. So what Bacon does, it has a core from, say, between 0 and 100 centimeters depth is divided into sequences, into parts, yeah, sections. And then the slope for each section is its accumulation rate, okay, or actually sedimentation time. Yeah, so that's the whole model. Yeah, and once you have this, you have the start age, and then for each section you have the slope, yeah, the accumulation rate. And then for any depth, you can find the corresponding age for that model. Here I've just plotted 3 iterations that each assign a certain calendar age to any depth around here, okay? So these divisions are of equal thickness, yeah, and the default is 5 centimeters. And the locations of the elbows do not necessarily correspond to where you have dated it, yeah? So you could have 100 elbows and 5 dates. Yeah, there's no relation between where the dates are and where the model is. Okay, where the model elbows are. So we divide the core into K sections of equal width or thickness, and the default of this thickness delta C here is 5 centimeters, and the elbows are C0, so the top elbow, and then C, which is of a smaller depth than C1, and then C1 is of a smaller depth than C2, etc., until we reach the bottom of the core, CK. Right? And then for each section J, we model the accumulation rate, X, of that section J. Yeah. Okay. Now, the age model, we call here G, it depends on depth, on the starting age, theta, and on the accumulation rate of the sections. Yeah, and that model is then defined as this. So we've got theta, sorry, I'll just stop using the little circle. Theta, which is the start age, this one here, plus however many sections you need to sum up until you reach your depth. For example, if our depth of interest is 45 centimeters, for example, we calculate this, until we are just reaching 45 centimeters. And then we just extrapolate a little bit more until the next section, and that's this bit here. Yeah. So for any depth, we simply use the starting age and then add all the accumulation rates of each of the sections until we reach the depth of interest. We extrapolate them between the last two section elbows, and that gives us the age for that iteration for that depth. Yeah. Okay. Any questions there? Well, I have a question. Do you think that's a likely model? Has our site accumulated like that? With linear or say piecewise interpolation or piecewise regression? Yes, no? So one thing is it's a bit strange that we have these little sections now, and within the sections it's accumulating exactly linearly, and then it's changing all the time between the just at the elbows, but nowhere else. Seems a bit strange, but given that we use this many times, in the end our model looks quite smooth in most cases. Sometimes if you have few sections, the elbows, you will see them. So one thing that we are working on now with my colleagues in Mexico is to produce smooth bacon. Yeah, because, well, you guys, you like crispy bacon. Over my side of the pond, it's more smooth bacon, more floppy. And we're producing something which will not be as like elbowy, is a bit more smooth. All right. Any questions there? Okay, let's continue. So now let's look at the priors then, yeah, because there are some questions about the priors. So the default of bacon is now 20 years per centimeter, that's the sedimentation times, right? It's a gamma distribution, which means it's always larger than 0. And the shape is by default is 1.5, yeah? So that's this shape here we see here. That allows for quite wide range of accumulation rates. So it could be 60, 40, 10. Many rates are possible. Yeah. And we can also set the shape to be something higher. So from 5 or 10, and then the thing becomes more peaked. So we have more information that it should be a specific value. Okay. So the default is 20 years per centimeter, but that doesn't mean that it always works, yeah? Because there's other sites that could have quite different rates, yeah? For example, if you have a recent site, which only just accumulated, you quite likely expect some faster accumulation rates than 20 years per centimeter. It could be 10 or 5 or even faster than that. Older sites might be more compacted and have lower accumulation rates. And then there's things like deltas, so accumulation sites that might go much faster than lakes or much slower than lakes. Ocean basins will possibly accumulate very slowly. So you have information from the nature of the site as to what would be a good prior for the accumulation rate. That's before seeing the data, simply by knowing about the sites that you're working with. Yeah. So before you pay for any dates, what do you think will happen with accumulation? Okay. So what happens when bacon loads a core? It quickly checks is the default accumulation rate of 20 years per centimeter? Is that more or less does it seem okay, or should we change it to a different prior? And if it looks to be much slower or much faster, then that could be accommodated by 20 years per centimeter, then bacon will suggest a different accumulation rate, and then you can accept it or not, or provide your own value. Okay. Here I'm mostly talking about the mean, changing the mean, But you can also change the shape. So if you have hardly any information, you could perhaps put your shape to even lower values than 1.5. Of course, you want to have like many different possible shapes or possible accumulation rates. But if you know a lot about the accumulation rate already, you can put your prior stronger, more narrow, higher values of shape. Okay. Now, once then the prior is set and once the data are available, then this MCMC run will combine the prior with the new data and produce the posterior. Yeah, so we update information. The model is learning about the process. It's learning about the accumulation rates and its variability in your site by combining what it knew already, the 20 years per centimeter, combining that with your data and to update our information. Yeah. So the prior is an integral part of this process. So we're talking about the accumulation rate only, and we'll come to memory later. Okay. Yeah. So the memory. So the memory tells us by how much accumulation rates could change from one depth to the next. Yeah. So you have a constraint on the accumulation rate. For example, it could be like very close to 5, but then there's also so how much accumulation rate could change from one depth to the next. Yeah. So there's another prior for that, and that's a beta distribution, which is a distribution which is always between 0% and 1 or 100%. And we've set the default for that prior, you can see it here, to be at 0.5, so half, the strength of 10. So this prior here accommodates for quite a wide range of possible values to actually exist. Yeah, so it's quite a permissive prior. If you know more, then you can add it more. Okay. Now, how does that memory? How does it work? We have to look a little bit at the mathematics then here. So, do you remember that Bacon works on sections, and it models the accumulation rate for each section? Yeah. Now, this modeling of the accumulation rate for each section, for example, section J, depends on W. Yeah. So it has two components. The modeled accumulation rate at any section depends on one part and another part. One part is the accumulation rate of the section under it. Yeah. So the next section. And one part depends on the prior of the accumulation rate, in blue here, alpha accumulation rate at section J. Yeah. So there's two parts. The accumulation rate at section J depends partly on what happened before and partly on the prior information on accumulation rate. And this partly, so how much it depends on it, that's W, that's the memory. Yeah. If your memory is very high, if it's close to 1, then almost all of the accumulation rate of J will depend on what happened before. Of course, if it's W is say very close to 1, this is very close to 0 then. So your prior information of accumulation rate is almost kicked out. And almost all of our information about the accumulation rate stems from what happened at the section below it. Yeah. So if W is close to 1, if the memory is very high, then XJ will depend a lot or almost entirely on the accumulation rate of the section below it. But if memory is close to 0, this whole thing of what happened before really doesn't matter, and any accumulation rates are sampled from alpha, from the prior information, and so that will then get you a much more flexible model. Yeah. Any questions there? No? Okay, move on. So how did we come on the prior for the accumulation rate? So originally in the first years of Bacon and of its predecessor BPEAT, it was based on, it was 10 years per centimeter. But Then Simon Goring et al. We analyzed so over 200 lakes and tidal wetlands in northeastern US. And the age models were produced using classical methods. And from the age model it was then checked what the accumulation rates or sedimentation times were. And if you plot them over time, there's a common trend, yeah. For very old sites, the position times are longer, higher, so slower. And then there's a long time over the Holocene where accumulation rates are around 20 years per centimeter. And then for more recent sites, we have deviations to more faster accumulation. And that's how we then decided upon getting 20 years per centimeter, and the shape as it appeared from this paper, from this analysis, the shape would be something between, of this gamma distribution, something larger than 1 and below, between larger than 1 and 2. Okay, so that's how we came up then with a mean of 20 years per centimeter and a shape of 1.5. Okay.
Hey, Martin.
Yes.
I'm wondering if I can ask a question about the previous slide before we move on.
Yeah.
So forgive me if I had to step away for a second when you started this slide. So forgive me if you said this, but is memory itself a prior? Do we enter prior? So that is because I'm looking at the output for
So the memory is actually that's this prior here.
Okay. So the memory itself is set as a prior, and it just varies between 0 and 1, or okay.
Yeah. So you could have, for example, a site. So if you have, say, if you set your accumulation rate prior to be something quite wide, but your memory to be something very specific, you could have a straight model. And that could then be, well, anywhere on here on the accumulation rate. Yeah. And so in most cases, I think the memory prior isn't in most cases that important. I mean, I think the default seems to be quite reasonable. Perhaps it's more important to look at the accumulation rate, but we'll come to that later, like combine or checking how the prior and posterior compare. Okay.
All right. Thank you.
Yes. Okay. So this is how the accumulation rate prior was set. So it's useful for many sites in northeastern US, and hopefully that will then extrapolate to other areas. Yeah, but it doesn't always extrapolate to other areas. Okay. For example, it wouldn't work that well for ocean basins, which would accumulate much slower in most cases. Which brings us to Mars. Yeah. So there's a paper which looks at remote sensing or remote photos of Mars from satellites that are orbiting Mars. And this paper here, Williamson and White 2014, was particularly interested in a basin where there seems to be, say, information in from what they see as if there used to be a lake. Yeah, a lake which was had sizes at different times. Yeah. And they're particularly interested in a few in fan F. I wouldn't be able to recognize this as a sediment fan, but that's this fan here. And based on the photos and the telemetry, they think that fan F indicates that there's around 45 meters of layered deposits under that fan. So around 45 meters of deposits have accumulated on that site in Mars. Now we can't really go and send a rover and then start coring. Actually, a good idea, and it has just been done, but not in this crater. We can't really get data, no? So all we have is 45 meters of sediment And then we have to somehow, if we want to know how long that lake should have been active for, we have to use some guesstimate of how much time is in 1 meter or in 4 to 5 meters. So then William and White used Goring et al. So the estimate of sedimentation times in northeastern US lakes to provide an estimate, a range of how long it would have taken for those 45 meters of sediment to accumulate on Mars. And that one was then between 4.5 to 230,000 years. Yeah. So what do you think about this? So no data, and we're using terrestrial estimates. We're extrapolating them to Mars. Yeah. And we come up with a range of what could have happened in Mars, but we are not using additional data. We're only using the prior information. Yeah. So bacon on Mars. So that seems to be a thing. You can have a recipe for frying Mars bar and wrapped in bacon. So why not? So on Mars, all we have in this case is the prior information. Yeah. And this is prior information from a different planet. Yeah. And we have no new data to learn from. So in this case, the MCMC process, if we were to apply bacon on Mars, if we had this 45 meters of sediment and we want to produce an age depth model, we have no new data. So all we know is the prior information. And we're assuming that we can extrapolate this prior information from Earth to a different planet. Yeah. And then we're using the MCMC process to randomly sample values of accumulation rate while obeying this prior. Yeah, because all we have is the prior. So that way you can then come up with, for 45 meters of sediment, a range of accumulation, of sedimentation times. Okay. Luckily enough, in real life, we do have, we're on Earth and we can go to sites and we can sample them and we can radiocarbon date them or use other types of data. So then we have new information which we can combine with the data we have already and then to update our knowledge. Yeah. So that's, for example, here then you have your core with lots of dates, way too many dates perhaps, and you combine your prior information you have with the dates, and then you arrive at the posterior information, which is the gray bit. Yeah, so you have your green prior accumulation rate, and the posterior is what came out after the modeling. And the same for the memory. Yeah. So that's how we should be reading these graphs. So we have the prior information in green, posterior information. So the actually the accumulation rates underlying this age depth model. And in this case, the gray and the green bits overlap a lot. Yeah. So we have a very good correspondence between what we see for the green one and for the gray one for accumulation rate, and the same for memory. Yeah. So what does it mean? In this case, we combine the prior information with the data. We got a model, but we didn't really learn much new about accumulation rate. Yeah. Our information about the accumulation rate hasn't really been updated. It's about the same. Same for memory. We haven't really learned much about how much this site varies in accumulation rate over time. It's more or less what we expected. What we did learn is the age model. Yeah. So we've got many data points, but it's an average site, and we didn't really have many surprises. We didn't learn anything new other than the age model, but we didn't learn much new. We don't have any reason to update our prior because it fits well. Okay. We'll come to the MCMC part later. Okay, so we had a look at the out file. So any course output file will have many columns. The first column is the starting age. And then for each section, by default 5 centimeters depth, will have the accumulation rates, the estimate of the accumulation rates. Yeah, and then the final 2 or 3 columns have to do with the fit of the model, and we don't really mind too much about that now for the moment. So it's this file that's then used to produce the HDAP model. Okay. Right. Now let's play a little bit more with the priors. For example, if we would use the other default core that comes with Bacon, RLGH3, and so Bacon would normally ask, should I adapt the mean of the prior to 50? Because initial attempts to fit the data seemed that from those additional attempts, it seemed that the default of 20 years per centimeter prior mean accumulation rate doesn't really work. But we say, no, just use 20. Okay? Okay, Bacon doesn't mind. If you say so, so it produces the model. It combines the prior information over an average of 20 years per centimeter. It combines it with the data and produces an output, a model. Yeah? Fine. Now, what happens here? So we've got our prior in green and the posterior in gray, and same here. And here, in this case, the posterior and the prior don't really agree. So they overlap, but there's a different shape between the posterior and the prior. Yeah. So we have now actually updated our information. We have learned a bit like, okay, so our posterior is a bit different from our prior. Yeah. At least for accumulation rate, but not really for the prior. For the memory seems like has shifted a tiny bit to lower values, but not that much. Okay. And if we look at the model, it looks fine. It is bypassing some dates, which are scattered, which tells us that not all dates should be trusted. Yeah, there's plenty scatter. And the model said, oh, you know what? I'm just going to ignore that lowermost date. It just doesn't fit with the prior that have been given. So I'll just go straight ahead. Yeah. Fine. I mean, that's what Bacon did. It tried to fit as much as possible the data with the prior and said, well, a few outliers, well, you'll just have to live with that, and it produces this model. Okay. Now let's run it again and instead accept the suggestion of Bacon to change the accumulation mean prior to 50, from the original 20 to 50. We do the same process. We combine the prior information with the data, and we get this model, which looks much the same. It also bypasses some dates, but now the lowermost date isn't an outlier. Yeah. So suddenly our model produces very slow accumulation rates in order to fit this lowermost date. Yeah. So now we have adapted our prior information, and we get quite a different model. Yeah. So in this case, what Bacon is saying, well, I think that this date is correct, and we should be assuming a very low accumulation rate for a few thousand years, and then change accumulation rate. Yeah. The memory has also changed a bit. It has become a little bit lower than in the previous example, because it has to make that bend to fit that other date. Yeah. So our memory, so how fast things can change from one accumulation rate can change from one depth to the next, will have to be updated a bit. So with this model, with these assumptions, we have learned a bit about the process. Yeah, so I hope that with this type of choices of priors, you can see that the prior information is actually an essential part of the Bacon process. Yeah, and it can be used to make decisions. You can say, you could decide that, for example, sometimes dates are simply wrong. Yeah, so we could go for this model and then accept a bit of scatter. but you can also think about the process in which this site was accumulating, and perhaps this is then a better model for this site than this one. Yeah, but there the knowledge of the user, of the expert on the site, comes into play. What is the most likely scenario? This one, or something else entirely? Yeah. So the model had to choose. Bacon had to choose between either kicking this blade out as an outlier and going happily straight on, because straight is better, because you, if you, the prior says like, oh, you just, if you can go straight, go straight. Yeah, or well, yeah, more or less. It's also this type of slow accumulation rate doesn't fit well, perhaps with the default prior. Sorry, this prior. So with the default prior of 20 years per centimeter, our site couldn't really accumulate very slowly. Yeah, so it just kicks it out outlier. But at a different prior, we don't have to do that. We don't get a penalty of kicking out a date. Yeah. Any questions here? Would we want to perhaps to take a quick break, because we've been going for an hour?
Yeah, that sounds good. Let's take a 4-minute break and be back at 12:07 or whatever 07 past the hour.
Okay, sounds good.
Only 4 minutes.
did you say 7 past the hour?
Oh yeah, that's right now. Get
Oof,
back to
so-
work.
So quick.
Yeah, sorry. And Martin, I think that if you're not able to get to everything that you intended in the next hour, that we can certainly stay on. Don't worry about, having to stop. We are recording so people can catch up if they need to leave.
Okay.
So
Yeah.
if people want to stick around and ask, look at models or wherever we get to, that would be fine.
Yeah. Okay. Right. Let's so if we then play with the memory prior, for example, we can have our RLGH3 core again, and I can run it with a very, very peaked prior for memory to force it to be around 1. Yeah, so I put a mean at 0.99 and the strength as like a ridiculous 1,000. Yeah, so we're just putting ridiculous values here just to see what happens with those settings. In this case, the ACE model is awful. Yeah, it is. The memory is so high that the prior information is not taken into account, and all it does is trying to draw more or less a straight line, not exactly, but mostly straight line through the whole site. And the model is bad because the prior is not good. All right. If we set, on the other hand, the prior to be very close to 0, which is, so the prior is very peaked at 0, then the model looks actually quite a lot like what we had with the default prior. So it's not bad. And in most cases, again, I would recommend just using this default setting for the prior, which is permissive. It allows anything between 0 and 1 and doesn't really give much, it's not very strong information. Yeah? And it's quite important to, when you have a site, check different settings of, for example, the thickness of the elbows and the memory, and just look if with different settings you get, with slightly different settings you get the same output. Okay. Right.
And Martin, sorry to interrupt, but there was a question about if you can go back to the RGLH3. Excuse me. What about that other set of dates that are kind of in a straight line between about 50 and 125? Like, why is there an a priori reason to exclude those? I mean, is the model just doing that? Like, why the other dates and not those? Is it just because there are more of the others? Is this prior information? Why, like, what about those dates? We're all looking at them.
Yeah, a good question. And I've never ever seen Bacon do anything else than choose this upper range of dates and never the younger dates. Probably because these other dates here, like they lie in a straight line and there are more. And if it would have to go through the younger set of dates, it would have to bend more here. And I think just it doesn't want to do that. But surely we should be able to find settings of the prior information that made the model go through these few. For example, I could imagine setting a very strong prior on the accumulation rates and then a break in accumulation rates and then different accumulation rates here. But that's really like fudging the data too much probably. But yeah, it's by far the most robust outcome, but the most robust model seems to be one where these lower or the younger dates are kicked out as outliers. Okay. I've done some more analysis just quickly of, say, using a totally different data sets and then putting the prior for memory to be very low or very high. And in this case, we see very similar outputs, but for some reason, when I put memory to be very, very high, and the ACE model is more uncertain. I'm not so sure how to interpret that, but again, that's something that you can do for your own site as well. So which values to choose? Yeah. For reasons of transparency and consistency, I would suggest that you use the default values that where possible, or if you make Bacon if you tell Bacon to accept the values that Bacon suggests, then accept them and use them, but tell so in the paper. Yeah, tell that you adapted the accumulation mean prior to 10 or 100 or 50. Yeah. And if you have more information about your site, if you know more about the site, you can adapt the priors. Yeah. So if you have a recent lake, you could adapt the ACC mean to be somewhere around 10 or so. For a glacial lake, it would be 50. Yeah. And if you have strong information about this type of accumulation rate, for example, a site where you have post-bomb dates, where you can see, where you have very strong information about what the rate could be, then you could set ACC shape to be very high and peaked. Yeah, because you have very strong information, prior information about the accumulation rates. For the memory, if you expect high variations in accumulation rate from one depth to the next, then you could put the memory accordingly. And the strength, if you have strong information about that memory. Okay. And again, test a range of priors, because your model should be robust. Yeah, robust in that if you run it several times, you get more or less the same outcome. And also if you change your priors to other reasonable values, that you get also again, more or less, comparable output. Okay, good. Now, if you have stratigraphical changes, for example, you have, some stratigraphical event at say 140 centimeters depth, and you have a totally different stratigraphy before and say below and above that event, you can then set different accumulation rate priors for above and below that event. So if your boundary at 140, you can set, for example, your accumulation rate prior for the accumulation rate mean to be 5 above that boundary and 200 below. Ridiculous numbers in this case, but that will then be taken into account, and then you will have a model that obeys the prior information and to some degree the dates as well. Okay, and you can also use a hiatus if you want to. So the same type of model, the same command, but then change boundary to hiatus.depths, and then it will model a hiatus. And the prior for hiatus is a uniform distribution with a maximum of 10,000 years, but that can also be changed if you want to. Okay, right, moving on. So now we have this other thing that affects your model, and that is, say, the thickness, the section thickness. Yeah, but the default is 5, and if you set your model to have too few sections, then the thing becomes too elbowy. Yeah, you see those elbows, and that's not nice, not smooth enough. So then you would want to decrease the thickness so you get more parameters and it becomes more smooth. If you have too many sections, that happens as well sometimes. If you have too many sections, then you have too many parameters, and then the model it's just too many parameters to estimate, and the model sometimes loses itself and becomes like a trumpet that just lives outside of the dates and is totally lost. In that case, you just have to reduce the amount of parameters by setting your thickness to something larger than it was, and then the model should be able to find itself back again. So if you're very, very long course, then the default of 5 centimeter thickness might not work because there's too many things, too many parameters to estimate, too many accumulation rates to estimate. So then different values for thick will be suggested. And for a very short core, where 5 would result in too few sections and too elbowy, then again, Bacon will suggest different values for thick. And later on, we'll look at Plum and their the default thickness is 1, not 5, because we're talking about these surface cores. Okay. So also when you testing different values, check what different values of thick do to your model. Okay. And sometimes if you have a very long core and it takes a long time to run, sometimes you can set the thickness to something quite big. So you have a few parameters only to model. You run a quick model and it might be quite elbowy, but that might be a good way to find the correct settings. And once you've found those correct settings, you can then decrease thick again to something which results in a smoother model. And currently we're working on finding better suggestions for how to decide on the thick parameter. In most cases that we looked at, 5 centimeters seems to work fine. That's more or less all I can say. Some cores have, instead of centimeters, have meters or kilometers even, and that can be adapted in your file. And some cores would work with millions of years instead of years. That can also be adapted. Anyway, now we also have to talk about MCMC. So the leftmost panel. And so what Bacon does, it runs all these millions of MCMC iterations, yeah? And the amount of iterations that you put on depends on the parameter S size, sample size, but also on the amount of sections or the amount of parameters you have. Yeah, and it will run, say, well, 5 million or 20 million MCMC iterations, and it does that using a special type of MCMC, so Monte Carlo Markov chain, or Markov chain Monte Carlo, and that's the T-walk. And there are many, well, there's a few different types of MCMC out there. And this one, made by Andres Christen and his colleague, is actually quite a nice one because many other types of MCMC approaches require lots of tuning. So you need quite a bit of knowledge in order to set the parameters for the MCMC. This one doesn't need that. It finds the correct settings by itself. It auto-tunes it. And it makes several types of movements in the space in order to get that. Now, it's a very inefficient process because of all those millions and millions of iterations, only less than 1%, often like 0.7% or so, 0.7% of the iterations will actually have moved a parameter. Remember that for each iteration, it will one random parameter will be changed by a tiny bit. And then this new iteration will either be accepted as a reasonable next model, or the fit is so bad that it will be rejected, and the previous iteration will still remain the same. So the rejections rates of the MCMC process in Bacon is really high. 99% of all the time you're spending, no parameter will be moved. All those iterations will actually they'll simply go. Yeah. And we only, so what we have at the end is a few thousand remaining iterations. All those others, they're not pointless. They're useful for the process of getting iterations. But we at the end have only a few thousand iterations. And after the run, there will sometimes be often be an initial burn-in where the model has found the correct settings, more or less, the correct parameters. And that burn-in is removed. And then additionally, more iterations are removed in order to get rid of any dependency, any structure in the MCMC output. And at the end of that process, what you should see is the MCMC plot should be like some white noise, and there with no structure or features. And if you have a run which has a burn-in or just shows too much variability, you can use functions like thinner to thin out the iterations, or scissors to cut off the initial bit or the end bit or a bit in between. So here we have a core that's where the MCMC is horrible. Yeah. So this is not what we want to see. You want to see a white noise process where there's no structure, except for perhaps this bit here. Yeah. So here the run didn't go well. The model is really finding its way, and it's just simply, it's not good enough. The mixing isn't good enough, and we should run for much, much longer in order to get something comparable to this white noise thing. Yeah. So this, I would never use this model. This doesn't look good. Okay. And this one is looks all right. And if you want to, you could perhaps cut out this bit here, but I wouldn't necessarily do that. Any questions? Okay. Now, another part of this MCMC process is its reproducibility. Yeah. If you run it once and then run it again, how comparable is the output? And one function that can be used for that is Bay convergence. And you can, what it does, it runs your core several times, for example, 5 times in this case. And in this case, we make it like a very small sample size, like a very short run. We repeat that process 5 times and put them all on top of each other in order to compare, to make sure that the individual runs don't disagree by too much, that there's not too much variability between the runs. If there is too much variability, like in this case, for these short runs, it says that, okay, I did 5 bacon runs, and the reduction factor, which is a comparison of how much these 5 different MCC runs overlap, say it's about 1.1 or 1.11, which is not good enough. So it should be, this factor should be smaller than that. So it says, well, not a robust run. So please try again with different settings, for example, more iterations. Okay. Right. Now, Amy, you had some cores as well. I quickly ran them. Swift current 41223. It has a mix of radiocarbon and CalBP dates, and also some lead-210 dates. And again, in your CSV file where you have your dates, you can include a mix of radiocarbon and CalBP dates by adding a 5th column where CC equals 0 for CalBP dates and 1 or 2 or 3 for radiocarbon dates. Okay. Anything else you want to add about this this core?
No, not in particular. I mean, it has, yeah, this was sort of something we threw everything at. It has lead-210. It has some tephra dates from the literature on identified tephras. This is from Glacier National Park. Radiocarbon dates, and then some VARV counting and extrapolation at the end, which I know is not ideal. I thought that if you were interested in showing well, everybody has the CSV file, but you could people could take a look at that and see how you identify which dates get calibrated and which don't. So with a 1 or a 0 in that calibration curve in that CC column. You can see that the radiocarbon dates, we have 1 for IntCal, whatever it was at the time, 14, and a 0 for the lead-210, the tephra, and any other of those non-radiocarbon dates.
And those are plotted in this weird, like, light blue color, and the radiocarbon dates in dark blue. We have a bit of a problem because Amora took over my seat. Amora,
yeah, you can't work anymore.
No, sorry, you have to cancel the session. No. Amora,
yep.
Sorry about that. Okay, now, and you can now also use Plum to redo this one perhaps, but we'll look at that later. Okay, the next one is Steel 98. And I just plotted, so it's got quite a large number of dates. And I plotted here the file because it contains more columns. Yeah. So this one has 5, 6, 7, 8, 9 columns. Yeah. So we've got an additional column for the CC, which we just described, whereas 0 is CalBP years and 1 is IntCal 20. And then we have additional columns for the reservoir effect. So if your date is subject to a reservoir effect, what do you think, Amora? 0, yes. So in this case, the reservoir effect is 0, plus or minus 0. And then we've got the final columns are for TA and TB. Oh, sorry. And that is for the student T distribution. And we'll come to that. Do we come to that now? So if you have a reservoir effect for some of your dates, you can include that as additional columns for your dates in your CSV file. And if you have different values for TA and TB, which we'll come to later, you can also include that here. Okay. Right. The student T. So what Bacon uses by default is not to model our dates using the Gaussian distribution, which is here in red. So if you use the Gaussian distribution to calibrate your dates, you get a distribution like the red one. But what we're actually using is by default. We don't use the Gaussian distribution, but we use something quite similar, the student T distribution. And that's the gray one here. It's very comparable to the normal distribution or to using the normal distribution, but the peaks are a bit lower and there's some more wider tails. And that's very, very useful because that actually allows for outliers, for a bit of scatter. So if a date is scattered, it still actually fits the model a little bit. So the student T has wider tails using the settings that we use of the two parameters A equals 3 and B equals 4. And that allows us then for a bit of scatter. And for example, the scatter that we see, where are we? For example, this type of scatter, yeah? That's the type of scatter that with normal, if you use the normal distribution to model the error of a dates, that would become a bit problematic. But if you use the student T distribution, which has wider tails, a bit of scatter can easily be accommodated. Okay. Right. So what the student T does, it is when we enter our dates, it has each date has a lab error, for example, 25 years or 20 or 50. And that's just one number. But what this student T introduces is a sort of uncertainty of the uncertainty. So we're not exactly certain that the error size that we assign to that date is the correct one. It could be less, it could be more. Yeah. So there's an error multiplier, and this multiplier of the dates error could be 1, but it could also be more. So and that's the student T distribution with 2 parameters, and we suggest you use A equals 3 and B equals 4. And that will produce a distribution which looks a lot like the normal distribution, but has these handy tails. Yeah. If you have some dates that you're very sure of that they are correct, that the error is correct, then you can put higher values, different values for A and B for those dates. Okay. Right. Now, for your own core, you can produce a CSV file with only 4 columns. So lab ID, radiocarbon age, error, and depth. But I would suggest to also add the 5th column, which is the calibration curve column, so that you remember which calibration curve was used for each date. Yeah. And you put that in a new folder under the umbrella folder, which is say Bacon runs. And then you call your core some name, for example, some Tefra core. And within the folder some Tefra core, you will have some Tefra core.csv. And then you will run Bacon to run that core. Okay. I hope you've been able to do that. We also had a question about depths, and I think Amy, you already discussed that in a mail that you can. There's several ways in which you can use other types of depths than the default ones. Yeah. So yeah, we can. If there's more questions, we can look at it again. But this should be enough. Yeah. Then we've got the post-run analysis, which we went through quickly. I really suggest that if you want to look at, if you're interested in accumulation rate history as a proxy, don't just use the mean, but also use this to look at the variability, the uncertainty of it. For example, by plotting your accumulation rate against depth or against time. And You can also please look at your proxies as a grayscale and not just one curve. Same, yeah. Okay, I think that's me for the moment. Are there any questions, or anyone wants to look at other cores, or would you want to have a quick look at Plum? What would you like? And Morda, what do you think? More, I couldn't care less. Well, you want to have a look at Plum? Yeah. Okay.
Yep, I
So,
think that would be great. And people can, I know that some people are messaging me and sort of asking some questions about issues with their, their bacon runs, and go ahead and keep doing that. We can do that, more of that as a group after, if you like. But
okay.
yeah, Plum would be extremely important, I think.
Okay. So what Plum does, so what led to 10 dating is that for radiocarbon dating, you have just one date, and that will tell you something about the absolute age of that depth that you're interested in. For lead to 10 is different. A single value can't tell you very much or hardly anything. You need to have a sequence of measurements for lead to 10. And there's also there's generally two components to lead to 10. What here in pink is, say, the background input of lead to 10. So the supported lead to 10, I call it. And then you've also got influx raining in of lead from the atmosphere through the water column into your site. And that's the one that we're interested in, because that one will decrease over time. Yeah. So what we're doing with Plum is we're using this forward model of that we know, well, we have an age step model, and we have the measurements of lead to 10. And what we're trying to do is to produce a model that accommodates the values, and yes, that tries to reproduce those measured values. Okay, so what it depends on, Plum assumes that the influx of lead to 10 is constant. That's something we could debate. But that's what most models assume anyway, but we could actually change that in future iterations. And it assumes either a constant or a varying supported background lead. Yeah. And then it uses the Bacon model to produce an age-step model. Yeah. So we assume for the measurements of lead to 10, we don't get rid of the supported lead. We just use the total measurements as they are measured in the lab. And each measurement, Pi, the lead in slice I, depends on the total lead in that slice. And that should be, we hope, distributed normally. That measurement should have a normal error based on the total lead in that slice I and some error. Yeah. And the total lead depends, it consists of both supported, PS, and unsupported, PU lead. And this PS, the supported lead, can either be constant throughout the core, then we have simply that the PI total is PS plus PIU, unsupported, or PS can also be varying throughout the core. Then we have PIT equals PIS plus PIU. All right. Now, so we're not getting rid of lead, of supported lead. We're using that as part of the process. Now, what happens now is that we, for each measured sample, each depth or each slice where we have a measurement of lead, we measure that, we model that as a normal distribution again, where we have a bit of the supported lead, the activity of the supported lead, which could be either varying or constant over the core. And we then also have the influx, which is constant again. Over the core, it's constant. That influx is here, phi. or phi. And then we have also the time, because we have a depth and we have an age, yeah. And the age model, the depth to age model, is our Bacon model, yeah. And if we know if we set a value for our supported, and we set a value for the influx, and we set a Bacon age depth model, then we know the entire, we know all the values, yeah? We then can calculate how much lead there should be in the top of our slice of interest and how much there should be in the bottom of the slice of interest, so that we can calculate the entire amount of lead 210 of the unsupported lead 210 that should still be in the slice at the time you're measuring it. All right, and we also add an error. So that's the whole thing. So it simply combines prior information on, well, it combines assumptions about this, the flux being constant, supported lead being either constant or changing, and then it applies the Bacon age depth model to give us all the parameters to calculate the lead value, the model it for each measured value slice. Yeah. So we can simply load or install our Plum, that's the name, and then we require it as before, and then run it, Plum. Yeah. And if we run the default core, simply using Plum, this one comes with just the PB measurements, lead 210 measurements, no additional radium measurements. So all we know about supported lead 210 is calculated from the tail, from the, say, where we've reached equilibrium. Now, this plot here has many subplots, but what we look at here is the little rectangles are the measured values, and the blue scale is the modeled values. And then in gray, we've got the age depth model. And then at the top, we've got the MCMC iterations, the accumulation rate of the Bacon age depth model and its memory. So these two make this model. Yeah. And then we've also got the values for phi, which is in gray the posterior, and in green the prior, which is very wide, so many things can be accommodated. And we've also got supported, which in this case is estimated based on the tail measurements. Yeah, so we've got parameters for supported, influx, and the memory and the accumulation rate, and that gives us the entire model and the modeled values for lead. Okay. In most cases, the modeled values do agree very much with the measured values, except for this one outlier here, but that happens. Yeah. Okay. So this is one core where we've just lead 210 measurements. If we also want to, if we also have additional measurements of the supported lead, for example, radium measurements, then you can assume those. So you can add that as additional information, which is here the purple data. You can add them and then assume that the supported is constant throughout the core, and then you get this model. You can run that with this command. This is another core that comes with our Plum as the package. You can also assume with the same data, you can assume that this actually varies over the core. So this is not a constant value, but it varies over the time or over depth, and thus over time. That takes longer to run because there's more parameters that have to be estimated. So if you can assume constant supported, it's often better because it runs faster and it's perhaps a safer assumption than in most cases, perhaps, than using these individual estimates. You also see that the model extends as far back as is safely possible, but when our modeled values start getting background values, then Bacon will not extrapolate beyond that. We'll say, okay, that's how far I will go and not beyond that. Okay. Now you can also, and this is interesting, I think, you can add other data. It's simply a part of the Bacon model, yeah? So our lead to 10 data are modeled with these two parameters and the Bacon model. And a Bacon model can simply get, you can add more information, radiocarbon dates or any other dates, and then it naturally combines, integrates all that information into an HDAP model. Yeah. So you don't have the problem of first putting your lead to 10 data through a CRS model and putting that into Bacon, because then you would be double modeling. Here, all the data is taken at face value and is accommodated based on the prior information and all of the data available to come as an integrated HDAP model. Okay, that's me. If there's any questions, or if people want to look at other cores or get more information about Bacon or Plum, I'm here.
Yep, we have a couple of questions in the chat, Martin. So one
Sure.
you just started to approach, which is why not just put the CRS? So we get from the lab, from the lead 210 lab, we get, you know, modeled ages for our lead 210. Why not just plug them into Bacon? You said you talked about double modeling, but can you talk a little bit more about why we would want to use Plum instead of just putting in the dates that come from the lab for lead 210?
Now, first of all, if you use Plum, I get more citations, and that's important. But it's also, the CRS model has uncertainties, yeah? For example, a CRS model can be very, very sensitive to what settings were used. For example, the simple process of taking away the supported lead, the decisions that are taken there can affect your CRS model by a lot. Yeah, I think in most cases, the CRS model is really underestimating that type of uncertainty. Much like classical HDAP models like CLAM underestimate uncertainty because they simply cannot accommodate all that uncertainty, whereas Bayesian models are more pessimistic but more realistic in their estimates of uncertainty. So Plum doesn't have to take away the supported lead, so that's one thing. Also, CRS requires the entire inventory of the core to be estimated, and if you're wrong there, then your whole model is wrong, and that has again to do with the supported data and taking away the supported data. If you have missing data, which is certainly a thing that can happen, you have to do all kinds of magic with CRS in order to fill in those missing gaps. For Plum, that's not a problem at all because it's just another data point. Yeah, yeah. So I think it's it's a more integrated approach, and it then can really combine the lead to 10 data and the radiocarbon data. It also puts the responsibility for the chronology in the lab of the user and not of the lead to 10 lab. Yeah. So yeah, that's more or less what I think it would be good to use Plum.
Thanks. I hope, Nancy, that answers your question. Another question is, so
sorry, so just one more, sorry. If it's also the amount of dates, the amount of data points in a CRS model, you have 20 or 30 data points. It doesn't, those are not 30 independent dates. Yeah, they all tell us something about the entire inventory of lead to 10, but it's not that these are 30 independent data points. But if you input them as a CRS output in Bacon, you get 30 data points, which Bacon thinks are independent. And mathematicians get totally crazy about that. That shouldn't be done. We perhaps couldn't care less, but I think it's important that you should have independent data coming into your model. Sorry for interrupting you.
No, that was actually a really, really good additional point about the differences between lead 210 and radiocarbon dates. So another question is, so radium 226 can be used as a background. What about lead 214?
that, yeah, if you have other types of background data, that should also be possible to include. I'm not so sure how you would do that at the moment. I'm not an expert on LED to 10, but if you have other measurements of background or say supported LED, then that should be able to include that.
Great. And a question, let's see. So, and this is a general question about extrapolation. So I understand that we are discouraged from extending our cores from our last date. In my case, I have a gravity core, which the dates are up to 20 to 25 centimeters. I'd like to extend this to the entire length of the gravity core, 40 to 50 centimeters. Is there a way to do this in Plum?
Well, it's a bit like Mars. No, you're almost without data. You're just using your prior information then to extrapolate. You're welcome to do that, but it's hardly based on data there. Yeah. So you're using Bacon on Mars, and you're not using the data there, but only using the prior information. I would recommend if you could get some radiocarbon dates, then you might be able to extrapolate, but then use some data to back up that you're extrapolating well. And one issue with the prior accumulation rate is that it will not, when it starts extrapolating, it will not really balloon or trumpet out because it is constrained by this green value. So it will continue on quite straight, but that might be an illusion because there's not really actually data to back that up, if that makes sense. So
Yeah, that's,
go
ahead.
So your best bet is to truncate where your data approach the limit of your measurements or of your the background.
Yep. And I think that a lot of the messages from all of this Plum and Bacon and Martin in general is just caution in presenting our data as knowing more than we actually do, and making sure that we were really presenting those uncertainties. Another great question is, does Plum use accumulated dry mass? It's important for the CRS model, and bulk density changes so much with depth at the core top.
No and yes. It doesn't use accumulated mass, it uses mass. It is somewhere in the equation. I think it's around here. So it is included in the supported, and well, yeah, so density is not accumulated mass, but density is one of the parameters that has to be included. And I'm aware of some cores where that data is not available, and that's a bit of a problem then. If we don't have that, we might have to, actually we could start looking at many lakes and see if there's some sort of a prior information we could use if we don't have that information. But you do need density or mass.
Yeah, other questions. Oh, can we see an example of a Plum input datasheet?
Oh yeah. Let me see where Plum. Good question. Can you see that? So
Yep.
this is something, so you have different columns. You have the lab ID as always. Then you have depth, then the density, followed by the measurements of LED to 10 and the error. Then the thickness of the slice, so that's here a thing. So the depth of your slice would be the, I always forget, the top of the or the bottom, one of them. I think it's the top. And if you have any additional data for background, you have, say, radium, then you can add them as extra columns. And then finally, you have the final column, which tells the date in AD or common era when it was measured. And then the case. So whether if you have radium data, would you want to assume them being constant, or oh, sorry, I'm now confused. That's probably this one. I'm still getting used to this to this file, but there's one value for what type of radium case to use, and there's also one value for how many tail data to use to help estimate the supported lead. Yeah, what so it's a bit confusing perhaps to have this order of columns, the depth, density, then the lead, and then thickness. So we might in the future change that to a slightly more logical order, but that might also cause more confusion than solve it. And if you don't provide the last column, Plum will ask you to provide it in the commands. So it will ask for the sampling year and so etc. And that will then be added as information to the file for the next run. Okay. Any other questions about Plum or Bacon?
I'm getting there. I think there's another question in the chat. Oh, I'm scrolling. Nope, that's just a thanks. I do have one question where someone's having trouble with the Swift current CSV file. Martin, did you need to do anything? It's an older CSV, and so
yes,
I don't know.
I had to do something. I think yes, I had to. I forgot to tell that. I had to change the name of the DR and the STD. It had a different name. I think that's what I did.
Yeah, okay, thank you. So trying that's the problem. So you'll have to just change those headers, and there should be information in the Bacon help. Where would he find that's so you can see what the headers are right here, but that should be in the Bacon manual. Where would you find that?
Good question. Is it
Or you could just look at the RLGH3 or MSB2K. Maybe those don't have all 7 columns.
They don't have all 7 columns. So
9 columns.
I don't remember if I have added that. It's a good point.
It's kind of funny because sometimes the simplest things are.
Yeah. So if you go to the vignettes,
there you go.
so there's these like little tutorials. If you go to folders files, then there is some information about what delta.r or delta std is one of the correct names you can give it. And then your other columns could be t.a and t.b.
Great, thank you. And sorry for sending out a file to everybody that was not plug and play.
Oh, that's good, because that's yeah, you can see the.
This is how we learn. And I think, can I share my screen and just compare? Sure. Well, okay, so take a look at this for just a second. This steel one, Martin, can you bring that to the front? Yeah, that's perfect. And I wanted to just show you in the paper that same age depth model. So it's the axes are flipped around a little bit, but this is the original from that Steel Lake paper, which again, the purpose was to once and for all set a chronology for the Minnesota pollen chronology history. And so this is, way back in the early 2000s, lots and lots of radiocarbon dates. And you can see that the way that each radiocarbon date is presented is as a calibrated date with just straight error bars, right? A little TIE fighter thing. And it doesn't capture that probability distribution function of the different possible ages. This is modeled as a Loess model. And so it looks very smooth, but you can see that, say, in between 2 dated horizons, it represents the uncertainty as essentially 0, right? And so if you had, say, a pollen transition in between 2 of these dated horizons, it would be presented as knowing that date very well, but it actually doesn't. So I've done a little, back when I started working with Bacon, about a decade ago, had an AGU poster where I compared, say, a bacon model to this model and how that would change the pollen transitions in the Minnesota pollen record. So it's interesting, and you can see that there are a few dates that are excluded, that they excluded a priori. There are a couple slumps. It's just an interesting comparison of sort of the best you could do pre-bacon and the different kinds of assumptions that that people make, and especially that presentation of uncertainty, where the whole idea was to improve the chronology, but there are still places where there's a lot of uncertainty that's not really shown.
Yeah, and look at the enormous scatter at the bottom as well. No, that's for the stool record.
Yep, and that is the trash layer. So something that happens very much in Minnesota and probably some other places where you have at the end of the Pleistocene, and you have still wasting ice sitting on the landscape, and you actually have lakes and forests developing on top of that glacier. And so when the glacier finally melts, you have this weird, you have the stuff under the glacier getting mixed with essentially a new forest. And that layer just has a whole bunch of, the trash layer. And so that's where that scatter comes from. Really interesting cores too, because they're varves. And anyway, it's all interesting. So what other questions do people have? Have you been trying to run anything that you're having trouble with? Have you run your own data and, been disappointed that your uncertainties look a lot bigger because the example, the MSB2K core has, more dates than anybody should really have? It's always a little disappointing to see the big balloons in our own data. But what other questions
as well?
So what other questions do people have about bacon or Plum? I know this is a lot, but hopefully the tutorials are helpful. But you may be getting stuck in just little places where, like Trang's question about just the column headings are a problem. So there are little places that you can get stuck that are very frustrating, but ooh, how can Randy interrupt a run that goes too long? Is there a break?
You can't. No, because we haven't in the C code that underlies, that does the actual MCMC, hasn't got an interrupt code. And I'm glad you asked, so that makes me, it gives me a stronger case for my maths colleagues to actually implement that. So yes, thank you. Interrupt code. Because he always said, no one needs that, but I think we do need that.
I think we need that. And how do you save results without exiting the program?
How do you mean? So the results are actually saved in files. So the output file and all the settings are saved. So next time you come back to your run, you can simply load the run again, and then you should have all the data available again. So there's no real need to save your results, but you can always, at the end of your bacon or your R session, you can always quit the session and save the data. So save the session, it's always a good thing to do. Then when you come back, you'll have the sum of the data still there.
Right, and that's sort of the commands where you're exiting and it asks if you want to save workspace image. And so that's like everything that you put in that command line. But you could just copy and paste that as well if you wanted to, be sure that you have it before you quit. Another command that I find, oh yeah, go ahead.
No, go ahead.
I was just going to say another command that I find useful sometimes when I've been running bacon for a while is I think it's bacon.cleanup.
Yeah.
Which just kind of clears everything. So sometimes bacon just gets a little confused.
Especially if for example, you've run a core and then you've like, oh no, actually that date was not at that depth, or you actually added some dates or removed some dates. Bacon can sometimes get confused. So if you've done something like that, like adding some different depths, just call bacon.cleanup, and that will then remove all the information it knows it has, all the runs it has done, and all the assumptions it has made for that core that is in memory. And then you can run it again, and it will then read the data all cleanly.
And Martin, is it capital B bacon.cleanup or lowercase bacon?
I never know that. I think bacon.cleanup. So it is a bacon clean up.
Ah, right. I forgot the parentheses. Does anybody want to share some of their data with us?
Oh, and this message pops up after running my data in Bacon. Warning, only 27% of the dates overlap with the A-step model. How concerned should I be about this message? Could you perhaps share your results? Share your screen? Because it probably means that many of the dates are simply not fitting with the model. So it possibly could be a bad run. Oh, that looks good. One, two, three, four, five, six, seven, eight, nine. 1, 2, 3, 4, 5, 6, 7, 8. 9 dates fit and 2 are outlying. I'm not so sure why it would say that only 20. Is it 72 or 27?
It's 27.
Okay, not sure why it should say 27. It looks larger to me than that. Could you perhaps send me the CSV file and the settings, the commands you have been giving? Then I can run it and see what values I get.
And this is great. One of the great things about Martin and Bacon and Plum is that all of your questionable stuff goes into improvements. Okay, Martin, do you see the other one in the chat? Are we encouraged to utilize? Yeah, go ahead.
Oh, sorry. Are we encouraged to utilize Plum instead of Bacon when we have primarily led to 10 dates? Since we'll be avoiding the double modeling from CRS model. Yes, please. Yes. So Plum is Plum, but it actually uses Bacon as the underlying A-step model. We could have chosen any other type. We could have used Clam or Bcron or Oxcal, but for some reason, because well, all of us together have made Bacon, so that's why one of the reasons that we used Bacon. So if you have primarily led to 10 dates, I would certainly use Plum. Of course, you can't enter led to 10 dates, the data themselves, the pure data, the raw data into Bacon, so you should use Plum anyway. But it's actually the same. If you install Plum or rplum, it actually also installs Bacon, and it uses the Bacon approach. It's the exact same code as Bacon. So it's just yeah, a subset of Bacon. Okay. Is there a Plum joke?
Oh, just the why it's Plum.
Oh, plomo, which is Spanish for lead, and then I thought plum.
It's very clever.
And there's also, if you are a vegan or a vegetarian, you don't have to use bacon. You can also use tofu.
That cracked me up so much. So you can do anything instead of the bacon command. You can use tofu anywhere.
Yeah, it should be fine. I don't have tofu cleanup or tofu.h.d, but it just runs fine.
What else? Great questions. We love the questions. Others, anybody else want to share a model that they've run that they think has worked well, poorly? Yeah, Jamila, awesome. You should be able to share your screen. Oh, and Martin, do you have to capitalize tofu?
No, lowercase. Don't know why. Didn't think of
Oh,
that.
what an interesting model. What can you, Jamila, what can you tell us about this model?
So this is on the lake I'm working on for my PhD dissertation. That's the Gore Lake in Willamette National Forest. So this one has, let me get, where is that one? So this one has like 12 radiocarbon dates with the VARFs counting. So the center one over here, this one is the Mazama eruption we had, and we were able to get 78 centimeter of Mazama tephra. And after Mazama tephra, like there is like two meter of the core, which has very fine lamination. So we were able to count like 660 VARs over the 2 meter, and we were able to get like 3 carbon dates in this particular area. And those carbon dates and the VARs counting were like, they fit really well with each other, which is confirming the VARs counting we did was correct. So, yeah.
Cool. Yeah, that's interesting because, wow. Because in most cases, if you have VARF counts, what you know is the relative time that has passed between different depths. But you do not know in many cases when it happened, but you know it in this case because you have the Tefron layer. That's really good. And then you have additional confirmation that from the radiocarbon dates.
Yeah, exactly. Like there were 3 dates at 3 different depths where we took the carbon dates, and they like pretty like they fit really well with each other. And these the VARF counting was done by myself and my advisor Dan Gavin. So it's kind of 2 researchers, they counted those independently. So confirming.
So you have an estimate of the error as well.
Yeah.
Excellent. Yeah. So one thing I would like to work on in future years is to include VARF counts that would be floating, for example. I still have no idea how we'll be able to do that in a Bayesian framework, but I think it's fascinating, and this is a really, really good case because you have the Tefron layer to anchor it. And how well do you know the age of the Tefron layer?
So the age of Tefron layer, we use the one, I think this was, I think the paper that came out recently. Dean, what was the paper it is? Can you remember?
Yeah, this is Dan. Oh, I forget the name on the paper, but it was a B-cron approach to aging the Mazama tephra using a whole bunch of dates and as upper limiting and lower limiting ages of the tephra. And they got it down to a like plus or minus 25 to 30 years. And I think, Jamila, if I remember right, that's what we used for the uncertainty on the VARF counts, was
That's
that same
correct, yeah.
uncertainty on the tephra. Yeah.
So that, yeah, so in an ideal case, in a decade in the future, there might be a model or an approach where that type of information could then be part of the modeling process. No, of course now the age uncertainty of that tephra is given as a date.
The calibrated age, yeah.
Yes, and then the VARF counts are given as calibrated data as well. But what in effect you have is you have a tephra layer with an uncertainty, and then relative to that you have your VARF counts, which should be a different type of error, if that makes sense.
Yeah.
This is the best you can do.
We just punted. Yeah, we just said use the same error as the tephra.
Yeah. But it would be something that we really nice to work on.
And then how many? We didn't put an age in for every VARV, of course. We did like every 10 centimeters, and that's arbitrary. too.
Yes, and indeed, if you would add one for every year, you would end up with hundreds of
Yeah.
thousands of dates, and Bacon
Yeah.
would be really happy and would just go through them. But there's some sort of an arbitrary number that you should put in, and that's I don't know how many, but that's sometimes similar. Sometimes people use Bacon to do tuning. So there's a record and where people align to, and they find then a few tuning points. I don't like tuning, but don't get me started on that. But then how many tuning points do you use? 2, 10, 100, 1,000? And the more you include, perhaps the more precise your age model is likely to look, but it's not necessarily true. So there's this a balance between how many data points you enter. Quite similar to that have led to 10 dating and using the CRS model. We also did some tests of using CRS model in adding it to Bacon of a simulated core. And if you use all the CRS data points as individual dates, the model was quite wrong. But if you take away half and then have fewer data points for Bacon to get confused by or use, then it actually got closer to the truth, because there was more freedom for Bacon to actually move around.
Yeah, it's really interesting. Thanks.
Thank you.
Yeah, thank you for sharing that one. That's a
really
really
nice.
cool example, that anchoring of our floating bar chronology. And it does, as I put in the chat, it reflects like how that sedimentation rate changes after the Mazama, which fertilizes, which not only you have the ash washing off the landscape for, quite a while, which is something we had in the Mazama in our Glacier National Park cores. So that contribution of ash over time, but also potentially fertilization with phosphorus and silicon that are coming from the ash. So if you're limited in that, you can have higher productivity after the Mazama as well, after a tephra. Good stuff. Other questions? I put a link in the chat for Martin's, if you want to get him started, you want to read about tuning. You can read that really good paper, which has good lessons.
Any other data that you want to share? Of course.
Any
And
other
that-
basic or very complicated questions about Bacon, Plum, radiocarbon, chronology, extrapolation, interpolation, uncertainty? Oh, we did have one question that I skipped in the chat, is about compaction. So loss of water so is compaction a factor at all in these models?
We're using depth, and so you perhaps say towards the very surface, you would have different apparent accumulation rates if you have lots of water in your sediment there. So there you would want to, for sites very close to a surface, you might want to adapt your prior to accommodate for that, not for the compaction or the non-compaction. You also might want to replace depth with accumulated mass, but that would be quite a bit of work perhaps, but that would perhaps get rid of some of that problem of compaction. But then you're replacing one problem of with another problem of that you get your mass estimates right, which shouldn't be too much of a problem. But I grew up as a paleocologist in Amsterdam with using depth and not accumulated mass, and that's what is in my brain. But I know that the Letter 10 community uses accumulated mass, so it can also be used. But we tend to use depth for these these models, except for Plum, where you indeed need to enter your mass as well. I hope that answers the question more or less.
Yeah, it's a tough one. There is some point after which, you know, in just a regular core that's not, you know, say a lake sediment core from the Holocene that's not under a ton of pressure or hasn't been, you know, squeezed by hundreds of meters on top of it. I think there is some, you know, there's at the surface, it's 100% water, and then it decreases over some depth, maybe the top meter, to whatever it ends up being, 70, 80% water, something like that. But then it's relatively constant below that, but of course changes with the characteristics of the sediment, the amount of organic matter, the grain size, things like that. So it turns out to be somewhat complicated. But yeah, the difference between linear sedimentation rate and mass accumulation rate is kind of at the heart of that. And lead 210 gets into that a lot, where you have to have the water content and the bulk density, dry bulk density of the sediment.
Yeah, and
thanks for the
if you have data, say sufficient lead to 10 data, or perhaps post-bomb radiocarbon data, Bacon should be able to capture any changes in accumulation as they take place. If there's enough data.
Yeah, that's a good point, that it sort of washes out in the linear sedimentation rate.
Anything else? My Zoom is getting very laggy again.
Yeah.
I can't see the new messages.
Nope, I think we're good. We're getting some thank yous and some examples.
Good.
And so I think we'll wind it up. Remember that these recordings are available. Martin's materials are available to you, and tutorials, and there's kind of more every day on especially on Plum, as it is, you know, continuing to be developed and refined and improved, both the model and the usability of the package. So stay tuned, and please fill out our surveys after this, whatever I'm saying.
And please keep the questions and remarks coming, because the more we get about possible ways to, as Amy is saying, to update our code to make it better. Would really appreciate that. Please.
Yep. The first email I ever sent to Martin after a short course, he responded with, "Yippee! I love bug reports." So that's kind of what you're dealing with. So thank you. Thanks everybody, and thanks to GSA for providing the foundation for this. And for any of you who are actually going to be in Portland, maybe we'll see you there. I will be there. So
when is it starting?
with masks on.
Next
the 10th of October, 10th through 13th. So we'll see. Might be not too many people, but a lot of remote participation.
So it's a hybrid.
Edward. Excellent. Yep, absolutely. Okay, thanks everybody. The recording will be linked on Martin's session 3 page at some point this afternoon,
probably tomorrow.
Or so.
Yeah, probably tomorrow.
Or tomorrow. It's later for Martin since he's in Belfast.
It's dark.
Okay.
Okay. Many thanks for all your questions, and thank you for bearing with me.
No, it's great. Thank you, Martin.
And Lisa. Thank you.
Okay, everybody have a great night, and we'll see you soon. Stay safe. Bye-bye.
Bye.